This is the first time that we were able to make this layer transfer without any defects. It happened quite early in my career, but that's been clearly powering the rest. We've been close to bankruptcy in 2015.
And then, if you look at all the great entrepreneurs, I mean, even like now, the most valued company is NVIDIA. Jensen, he nearly went bankrupt twice or three times.
I think the being close to bankruptcy is really accelerating the growth to the adult time. To win, you need also to hate losing. Every day was very difficult. So I think there is a strong willingness not to be there again. The most important I've noticed in the time is the ability of a team to gather to one common goal, which is make the company great again. And within 2 years, from 0% to 100% gallium arsenide to silicon. That was one of the structuring events to get the borderless phone. We allocate 25% to the long term, 75% to the 5 years. And we never change that ratio. Whatever happens, we keep it. We keep that allocation of money in the long run. The number one motivation is CO2 emission. The problem remains the same. So we need to stay strong on what the direction has been taken. We've seen some application in the world where you get some cameras or operating for 2 years without battery, and that's due to this unique capability. So in power SOI, you can make smaller die, and you can make them closer to each other, and maybe you can have die up to 50% smaller, which is huge in terms of cost saving at the end. We did not qualify one process that was really bringing performance. Cost was okay, but it was not really okay in terms of the impact. So we did not use that technology. In the SOI, we use up to 10 times the initial wafers. In compounds, we look at using more than 20 times the same wafer.
Today, we speak with Dr. Christophe Maleville, CTO and Senior EVP Innovation at Soitec.
A distinguished leader with a remarkable career spanning over 30 years in advanced material engineering. Highly respected in the industry, Christophe brings extensive expertise in translating fundamental material science into high-volume manufacturing solutions. His dual role as CTO and Senior EVP of Innovation highlights his significant influence on the company's long-term technology roadmaps.
Prepare for an insightful discussion on navigating the complex challenges of power-efficient computing and the critical advancements driving semiconductor acceleration from the heart of Europe. Let's dive in.
Hello and welcome back to the Semiconductor Leadership Podcast. I'm your host, Salah Nasri, and whether you are an industry veteran or someone who's just curious about semiconductor manufacturing, this is your podcast. First of all, I'd like to say a sincere thank you to all of you. We've just hit that 3,000 subscriber mark, and the hours that have been watched at the show has been absolutely remarkable. So I'm glad that you find it of value. But the interesting thing is when I look at the back end, we have more than 100,000 views on the program. So with 3,000 subscribers, that's just 3% of all of you who are following the podcast. So I ask a very simple, sincere favor is hit that subscribe button, because the more subscribers we get, the more powerful the platform will become. And I'll be able to get great interviewers and like our guest today. So without further ado, ladies and gentlemen, I hereby welcome you all to Christophe Maleville, who is the Chief Technology Officer and Senior Executive Vice President of Soitec's Innovation. He joined Soitec in 1993 and was a driving force behind the company's joint research activities with CEA Leti. He also, for several years, led the new SOI process development, oversaw SOI technology transfer from R&D to production, and also managed customer certifications. He also served as Vice President SOI Products Platform at Soitec, working closely with global customers. Christophe has also authored or co-authored more than 30 papers and holds some 30 patents as well. He has a PhD in microelectronics from Grenoble Institute of Technology and obtained an executive MBA from INSEAD. Without further ado, Christophe, welcome to the show. Great to have you here.
Yeah, great to be here.
Pleasure. Christophe, I would like to start off with some rapid fire questions, first of all, just to get the audience to know you. I've known you for a decent amount of years now, so I think it'd be nice for them to know. So let's hit them one by one. First of all, what's the first thing that comes to mind when you hear the word innovation?
Bring new values to people and everyday life on the people, and make sure that this electronics that we are using more and more can bring even more on a daily basis.
Sure. Silicon or SOI, which changed the game more?
Well, difficult to do SOI without silicon.
Yes.
So we are trying to push more the silicon by putting it at the right layers, preparing it for more performance. So, silicon first, but then SOI has pushed the limit further.
One word to describe your 30 plus years at Soitec.
Passion.
Nice. Patent or paper, what's more satisfying to publish?
That's a tough question. We get more from paper because it's immediate, you can see it, but the foundation's coming from the patents for sure.
Fair. What was harder, your PhD or INSEAD MBA?
Or INSEAD MBA, because going back to school after you left it for 17 years or 15 years is like impossible.
That's fair. Christophe, are you a morning person or night owl?
Neither.
Night owl?
Oh, yeah.
Okay. That's because of the work you have to do with Asia most of the time, or?
Well, no, but it's difficult to start in the morning.
Fair.
I'm born at the end of the day, so maybe that's the reason.
What's your favorite spot in Grenoble to recharge?
Right now is golf.
Golf.
Yeah.
Okay. The best piece of career advice you ever got?
The best piece of career advice?
Yes, you ever got.
Wait 48 hours before you react to something that's pissing you off.
Yeah. Wow, that's a fair point. 48. The version I've heard is 72 hours. Wait for 72 hours, and then pretty much the same thing.
Yeah, the French people are always more, 48 hours want to be quick, so.
That's nice. All right. If you weren't in semiconductors, Christophe, what field would you be in?
What field?
What field industry would you be in?
Out of the semiconductor?
Yeah, if it wasn't semiconductor.
I think performance sports.
Performance sport?
Yeah,
like running?
Like
triathlon?
Racing cars.
Racing cars?
Yes.
Okay. Favorite way to explain what you do to non-engineers?
Compare it to food.
Compare it to food.
Yeah.
Well, I'm going to question that further in the podcast. Coffee, tea, or something stronger to power through late nights?
Matcha.
That's your time in Japan,
exactly.
I presume.
Yeah.
Right? Okay. The proudest moment of your career so far?
The most important one, you mean?
Proudest, yeah.
Proudest? Well, proudest, if it comes long time ago, but this is the first time that we were able to make this layer transfer without any defects. It happened quite early in my career, but that's been clearly powering the rest.
Well, one technology trend that keeps you awake at night?
Wow. That's a tough one, but I would say AI and the how to bring this high quality, high value adding to the people, but how to compensate for the huge energy spent.
That's fair. What's more important, scaling or efficiency?
In our days today, I would say efficiency.
Yeah. From your perspective, two technologies, which one excites you the most? AI chips or quantum chips?
Or AI chips, because quantum chips is for tomorrow.
Yeah.
But today, AI chips.
AI chips. If you could collaborate with any tech leader, past or present, who would it be?
That's another tough one. Seeing the field where we are operating and seeing the personality of the guy, I would say Steve Jobs.
Steve Jobs, yeah.
Yeah.
Wow. Have you met him? No.
No.
Not yet. Fair play. What's your favorite book you recommend to colleagues?
There's one book called Good to Great.
Great book.
Yeah.
I love that book.
That's a great one in terms of
fantastic
managing and considering the people in your team and how to bring the best efficiency within the team. Sorry to interrupt.
Please.
I'd like to put another one, which called Even Elephant Can Dance.
Even Elephant Can Dance. Okay, tell me more about that.
It's been, I forget his name now, but it's been written by the CEO of IBM.
Mm-hmm.
And that's a great one.
Even Elephant Can Dance. Okay.
Yes.
Why? Why is it so special? I mean, Good to Great, I know back to back, but...
So special because the guy takes IBM. He has to solve the question of do we stay in the fabless or manufacturing? He has a fantastic position, and he's explaining inside how he is lost and feeling alone sometimes, and how humility is so important to whatever the position you have, and be able to get that time with very humble, that you think about the decision you have to take, but in front of the people, in front of the outside, in front of the investors, you have to get this very sure, no doubt position. And I think this duality described by such an important person is very, very, very
humbling.
Very humbling, very structuring in terms of that.
Chris, what's the single biggest misconception about semiconductors?
Wow. Well, I think I touched it a little bit, and but the huge power consumption and some of the paths that the semiconductor is taking right now versus the impact on the planet is some of the big question.
Okay. And 3 words to describe the future of semiconductors.
Green, efficient, accessible.
Green, efficient, and accessible. Yeah. That's a good one. Huh? Soitec, they're going to change the code mark, right? That's pretty cool. Of course, that's scalable on a global perspective. Awesome. Thank you, Christophe. So that's for you, ladies and gentlemen, who don't know Christophe. At least you can get a bit of a taster. But Christophe, you joined Soitec in 1993, and you helped drive joint research with CEA Leti. What would you say were the pivotal moments that shaped your path from process engineer to CTO and SEVP of innovation today?
First of all, the passion. The passion came from the beginning, as I said in the quick fire chat. Quite early in my R&D, I've been very lucky that I could demonstrate this zero defect transfer of the layer with that hydrogen, the smart cut we are using. It's been really driving some confidence that I can change things from what I'm doing. And then quickly we had this boost in terms of deploying the technology, and then I moved to the product. The move to the product has been very key, meaning that seeing the the impact and the transformation of this technology you're developing and bringing it to a product, and then being challenged by the customers and see how we can bring things that are bringing value to them. That's a very key moment when we realize that. To be more precise, there's been this AMD Intel kind of challenge in the early 2005, where when we were delivering our products to AMD, in one generation they were able to outperform Intel, and then the next generation Intel was coming back and so on. That was very exciting. That's been a very important time. But then combining that with personality, I was willing also to be able to drive some decisions, and I saw that I needed to reach the business. Another pivotal moment is going to Japan. One of my bosses said at that time, I had two bosses. One said, you need to go back to school and learn the business. Another one says, you need to go to sales because you need to learn the business, but in two different ways. And I had this opportunity to go to Japan to be the head of sales for Asia. And the way Japan is considering the technology and the sparring partners we had there in terms of being very much challenged has been structuring me for my career for sure. And the last point I would say that's super important, I do believe, is to be in a difficult time. We've been close to bankruptcy in 2015. Wow. We were in electronics, we went to solar, we went in LEDs. We saw the difficulty in fighting and competing with China at that time on some other arena. And I think being close to, I don't think it's needed to anybody, but when you start in a startup and you're growing, I think the being close to bankruptcy is really accelerating the growth to the adult time. And it's a super important moment in terms of a career.
Yeah. Now, do you feel, I've experienced it twice, unfortunately, close to. But when you reach that level of low, and then, if you look at all the great entrepreneurs, even like now, the most valued company is NVIDIA. Jensen, he nearly went bankrupt twice or three times. And especially there was a situation where the Sony saved him, right?
Yeah.
I think it's a kind of a theme that people have to go through as part of growth. And not only that, not necessarily that they have to go through, but it brings out a certain fire in the team, even though it's quite a stressful form of fire, but you actually end up being very creative and do things that you didn't do normally. Is that what you guys experienced as well at that time? Or?
Well, yeah, but trying to learn from every moment, every event. I think the two things I would get from that is one, being once there, you know how, or maybe you learn how to stay cold even when it's getting tough sometime, and it's learning that that there's always a worse situation. So I think it helps also driving the teams. But another lesson also is like, to win, you need also to hate losing, and being there. We did not bankrupt, but the company was really in a very tough situation, and every day was very difficult. So I think there is a strong willingness not to be there again, and that it's helped also shaping the motivation and the passion in every day.
But in that time period, you going back into that situation, did you see a change in behavior from people? Did you see more desire, more fire, more motivation, more inspiration, or was it more fear?
No, there was the fear. Okay, well, if we summarize very much pretty much the human being going with eros or thanatos, so you do what you like or you do what you fear. You don't do what you fear. So, but the most important I've noticed in the time is the ability of a team to gather to one common goal, which is make the company great again, and that that was the best time I've seen in terms of collective efficiency. So I think that's the big learning. Was it a fear? Yes, for sure. There's collective fear of everybody that is going over any politics, any other different agenda. And that's where you get the most of the people. Then the question is how to get that into the growth part without any fear behind. But I think that's part of growing also in terms of management of the people.
But when you look at that time moving forward, Soitec has had some very remarkable years after that situation, right?
After that, yes. Yes, clearly.
Yeah. Yeah. I want to talk about from the perspective of from lab to market. So early on, you led the SOI process development and R&D to production transfers. What would you say were the key lessons that you learned about turning breakthrough materials into reliable high-volume products?
Well, the positive lesson is like, I touch it a little bit, but that with the development in the technologies and pushing the limits, we can bring some value and make a change into the customers. Mm-hmm. The learning on the more negative side has been what has been 2 or 3 dramas into the 30 years where you create a new technology, it's like it's not exactly perfect, but you push for the transfer because you like it. The problem, the biggest problem of engineers is they like what they do. Mm-hmm. And there's this technology push, and then you get a massive return on the product. And I think the learning is that everything has to be perfect, basically, and nothing under the carpet, and it has to be proven with a champion. Mm-hmm. That's for sure. So the number one learning is go prove the technology with 1 or 2 champions that are really proving it, challenging everybody, all your specs. That's what we've done with some of the Japanese, as I mentioned, really pushing to the extreme, to the limits. Mm. And the other learning is to work to the end of the supply chain. When we recovered and made a very successful model for the company, it's really when we looked at our customers as close as possible to the system. What can the material bring, and then make it happen?
Yeah. What would you say was like the hinting moment, that moment of saying, right, this can be scalable? What procedures did you and your team consider?
The RF story for us is the most, I think, remarkable one when you get silicon that's working well for most of the device, but when you go high frequency in the RF for the smartphones and so on, it's not working. Mm. And we push the limit, we push the performance higher and higher and higher into the Silicon-on-Insulator for RF. At that time, competing with gallium arsenide. Yeah. Gallium arsenide was on the smartphones. All the smartphones were running on gallium arsenide for the switch and some of the front-end module elements. And suddenly, we get the performance good enough into the silicon, and within 2 years, from 0% to 100% gallium arsenide to silicon. So the clicking moment has been, you got to get the performance good enough. Yeah. And then everybody switched from the 3.5 to silicon. And at some point, that was one of the structuring events to get the borderless phone.
Yeah.
Because then now you're going across the world with one phone. You're not wondering if you are renting one when you arrive and so on, which was not the case in 2011, 12. Mm-hmm. Then the switch to silicon has allowed the designers to really integrate all the different bands into one chip. And it was a great move. But that move came part of it in terms of being able to increase the performance of these engineered substrates.
Okay. As CTO and head of innovation, I'd be intrigued to know, how do you prioritize the materials roadmap across markets? As you mentioned, with mobile RF, of course, with automotive, compute, power, photonics.
Well, first of all, we are developing technology platforms, and then from these platforms, we are fine-tuning products for the different segments. We have I would say, a basic way. We look at the cost of the developments, and we compare it to the possible revenue and in the different segments. So typically, we look at the cost to the production transfer, and we compare it to the revenue 5 years after the transfer. And that's the way we prioritize our development. Then there are champions as well, where we've been working with these very strategic customers for years. And that's the second way. So meeting the CTOs of these strategic customers on a regular basis, it's also a way to prioritize what's important, what's not, where to put our money, because we trust the directions they're giving us.
Yeah. So how do you then balance long horizon research with nearer term productization and customer certifications?
That's a very interesting question, and a very simple way. We allocate 25% to the long term, 75% to the 5 years, and we never change that ratio. Whatever happens, we keep it. We keep that allocation of money on the long run, and keep that direction. I can tell you, in the years where we talked about it, in the years where the revenue was not there anymore, and we had some challenge in terms of the company. Of course, the long-term technology effort has been stopped. It takes a very long time to recover. Basically, then you have a hole into your product. New products coming that is very difficult to correct. So it's very important to keep the long-term innovation, the long-term R&D protected.
When you refer to long-term, are you referring to being like as an early adopter, as one would say?
I think good or wrong, but we put a 5 years horizon to this short, medium term compared to long term. Everything that's more than 5 years, we are managing differently with a dedicated allocation. Then something that has changed recently is we saw that trying to refine the model, we saw that only an abrupt limit, like less than 5 years, more than 5 years, is not dynamic enough for the market. So we created incubators. These incubators having the challenge and the task to bring some of the longer term faster and with a different focus, because we believe that like everybody, we believe that the value we're bringing is bigger. They can make a bigger of a change, but we need to accelerate. So we changed the rule a little bit on 4 different topics. That's what has been done recently. But at the beginning, this is business units roadmap, 5 years horizon. We allocate some part of our innovation, and we protect absolutely 25% for the long run.
So, all right, let's pick an unfortunate circumstance.
Yeah.
And I'd be intrigued of how, with all the longevity you've had in terms of the industry experience, how you would deal, or how you've decided to deal with it. So, for example, just like us, we got into the power semiconductor field. We put a lot of effort in the silicon carbide world. And aside from China, we are seeing challenges in Europe and the US, mainly in the US. Europe, we're okay. But in the US, we're seeing huge challenges. From your perspective, how would you deal with a certain situation where you had, because what I can remember for us, 2023, even maybe last year, 2022, were magnificent years.
Yep.
Especially in the silicon carbide world, and now we're seeing a little bit of a shakeup. how do you deal with a certain scenario like that is quite challenging? Because I'm sure you had the same plan 5 years ago.
But we are clearly in the same scenario. We developed. We have power SOI. We have silicon carbide. We are developing gallium nitride. So we are in the same scenario. Then, first of all, we try not to forget the basis. The basics is why is silicon carbide appearing when everybody was running on silicon pretty well, right? The number one motivation is CO2 emission.
Correct.
So at some point, this remains. And I think the difficulty in terms of the cost, the difficulty in terms of the adoption, the economy for the car industry has temporarily delayed it, but the problem remains the same. So we need to stay strong on what the direction has been taken. That's number one. Number two, it's a topic that's very much discussed. It seems like also there is two markets appearing. And so as every company, you want to, every company in Europe at least, we want to compete in the US market and be able to serve also the Chinese market. So these two supply chains are existing and we are keeping developing their technologies to bring values in these two markets. In a difficult time, of course, we scale. We shrink a little bit the effort we're doing, but still balancing what's the next 5 years and what's the long term. So still developing the version N+2 for the long run, protecting the one we are, refining the one we are delivering by lowering the cost, but preparing the next step, preparing the higher voltage, preparing the gallium nitride in different shapes, because they are going to be so important materials to make sure the semiconductor is coming as a solution for the planet and not as a problem.
Yeah, that's fair. It's a very fair point. When I do my research or do analysis on the trends and etc., you hear multiple perspectives where some would say, it's done, and someone would say, no, it's going to come back and be resurrected and come back again. But I think what you've beautifully made very clear, Christophe, is that the problem is still there.
Mm-hmm.
And there is a need. It's just a matter of how urgent that need is. And will the time come when it is really urgent? That is the risk, I think. So how do you deal with risk in that perspective? Is it a perspective of just go in or mitigate the risk? Or
well, like every company, first of all, we look at how much cash we're spending and how to minimize that spend and make a plan on how we go the next 18 months. But always make sure, of course, that we have this value boost coming, and that what we are doing is still valid, even in a tougher market. So it takes time to bring the technology. The slowdown into the automotive industry has made that time even longer.
Yeah.
But as I said, the pillars are the same, the values are the same. We need to bring some material that has a cost benefit at the system level, that's for sure. But that also has a very positive impact in terms of the environment. So that these are two elements that are still valid and that we are working on.
Fair. Going into the engineered substrates and SOI platforms. So the SOI evolution. So for people who don't know what SOI is, can you give us like a brief explanation?
I'll try very brief. So SOI stands for Silicon-on-Insulator, which actually is a silicon and insulator on silicon. So I talk about food, but it's kind of a ham sandwich where we bring some ham and butter on bread. But clearly we isolate the active layer. The silicon active layer is isolated from the base substrate, which is a mechanical silicon support. By isolating that layer and playing also with this silicon dioxide, which is the insulator, we can bring more performance, less power consumption, and we can give more leverage to the designers and to the users on how they're going to engineer the resistivity, the capacitance of the device, and be able to have some different knobs in terms of optimizing the device. Typically, a customer takes a silicon wafer and a bare wafer and is etching, depositing, and creating chips and functionalities. We deliver that silicon layer, active silicon layer, that can be different from the underlying silicon, by the way, so that they can have some different option in terms of design.
And how has Silicon-on-Insulator evolved from early generations to today's FD-SOI and RFSOI?
Well, that's a long way. So we're going to make it magic in a few seconds. But the beginning has been clearly performance-oriented. People at the beginning realized that by isolating the silicon from this thin active layer from the rest of the bulk, there was clear benefits in terms of the charges management, because any charge that is creating by interaction with the air, ionization, and so on, could kill the device. But in an SOI device, it's not working this way. So for space applications at the beginning, when a lot of charges are created by alpha particles and so on, and ionization into the silicon, then SOI is behaving very well. But then when people, or in nuclear environment, for example, and that's why Leti also was, and CEA was really pushing for these developments. But then people realized by analyzing the devices that there was a kink effect. So it's a little bit technical, but it's very important. When you increase the voltage into the transistor, then there is at some point a performance boost that is appearing. And then IBM guys have used this performance boost to use that into high-end servers or graphics chips or AMD processors and so on. That was really the first wave of the SOI using this performance acceleration. Then we realized in 2015 onwards with the RF, but most importantly with this capability to choose the silicon and design the different layers we put inside, that we could address charge trapping, we could address different interfaces, we can address different orientation on the silicon versus the rest of the bulk, that we can bring a lot of advantages, being able to lower the capacitance a lot. And capacitance is something that is preventing you from being quick on a device. A capacitance is something, when you start pumping charges, you need to load this capacitance before you can do anything. In that time, this is time loss in terms of the reaction time of a device. And then we came from this performance to, I would say, performance, power, and cost optimized devices working together with the customers, where we can bring speed, low capacitance devices, low power devices, optimizing the structure.
And where do you see the biggest performance wins?
Well, clearly the biggest performance wins historically remains in the RF we talked about.
Yeah.
When you operate very high frequency in a silicon, you create charges into the insulators, into the silicon, and then close to the oxide. And when we brought this charge trapping into the structures of our RFSOI, clearly then suddenly we made it possible to have high frequency devices made on silicon with all the integration, all the legacy that exists in the silicon and has been boosting the front-end module integration in the past 10 years. That's the biggest win. Now, when we look at the most recent ones, the two biggest wins have been able to really tune the thickness uniformity of that active layers at the angstrom level. So we are delivering in FD-SOI plus minus half nanometer, all wafers, all points in hundreds of thousands of 300 millimeter wafers, and that's how the people can then do this planar, fully depleted device. That's one. The second one is in the photonics, where combining the thickness uniformity and the very low roughness into the oxide, we can bring into one platform all the waveguide, basically guiding the optical signal into the system, but also then building the electronic chips into the same platforms and having this perfect integration between light and electronics into one silicon wafer.
Marvelous. So I love the way you explained that. So if we look at like FD-SOI versus alternative CMOS paths, in low power compute and edge or automotive, where does FD-SOI uniquely outperform alternatives? And also, if you could also provide us, what is the remaining challenges that's available?
Well, where the physics helps, it's as I said, FD-SOI is a very low capacitance structures in terms of the device at the end. So this ability to switch on, make the functionality, then switch off, is unique to FD-SOI because it's such low capacitance that and thin films that you can operate in very low voltage. Wake up, do the functionality, make a measurement, send it through Bluetooth, and go back to sleep. So meaning that we've seen some application in the world where you get some cameras or operating for 2 years without battery, and that's due to these unique capabilities of FD-SOI with very low capacitance, very low voltage. Then when FD-SOI really shines the most, I would say, is in ability to work very high frequency. You can have devices operating at more than 100 gigahertz, and so for radar application, for example, this is where the physics of the structures is really making the most. So people naturally compare FinFET and FD-SOI. That's been forever since it's been invented. And clearly now there is a clear separation. FinFET delivers a super performance. We have it in all our smartphones. This is operating with a high current and high computing power. FD-SOI comes more as if you need to make very fast operations or very high frequency operations at low power. That's where FD-SOI brings something that FinFET cannot accomplish, and in a very planar, simple way. The third element, because ability to power on, do the job, go back sleep mode, that's one. Second is operating high frequency, low power, that's two. It comes from the physics of the FD-SOI. The last one is the natively, as I said, SOI is a very low soft error rate. Even if you get radiation coming to the device, and we have radiation everywhere, you have a separation from the device to the bulk of the silicon. So the high amount of charges that are generated into the volume of the silicon doesn't go to the device. And for that reason, there's very low soft error rate. So in most of our cars, not to say in all cars, there is two devices for one function, right? There is redundancy to make sure that if one is failing, the second one is not failing. In SOI and FD-SOI in particular, you don't need that. So at some point, you can have one device instead of two because of the much higher reliability of the device. And for microcontrollers generation that are now heavily powering our cars, I think that's a big advantage. That's why also FD-SOI is very much used for microcontrollers.
I see. So what about RFSOI for connected devices? Like, what substrate innovations are most critical for next-gen RF front ends, 6G, Wi-Fi, ultra-wideband, in terms of linearity, loss, and integration?
Yeah. So there's been two phases in the RF world. So 2013-14, we bring the performance of the RF chips up by trapping the charges, and then we were able to be good enough versus the gallium arsenide, and it's been replacing very fast. And then as there's been more and more bands covered by the device and more integrated into the same chip, since from 2014 to 2023, there's been more and more square millimeter of SOI in our smartphones. Okay? Now there is a form factor challenge. Our phones have more screens, more functionalities. The weight is a problem, so the battery cannot be expanded forever. So the second phase now of the RF device is to scale. So the RF device that were done into 110 nanometer or then 90, then 65 nanometer are now going 40 and maybe 28 in the future. But this is where the lithography challenge is getting more severe. And when you add more and more layers of polysilicon, oxide, different type of oxide onto your bare wafer, you need still to be compatible with the scalability and scaling the device. And they need to be compatible with 40 nanometer, 20 nanometer. So now we are pushing more on the planarity and the lithography specifications of our substrates. And that is what is driving now the development of a RFSOI device and substrate. So the engineer substrate have to be more compatible with advanced lithography nodes.
And of course, when you look at the smart process transfer, you oversaw the technology transfer and customer certifications. What best practices ensure consistent wafer uniformity, defectivity, of course, as nodes and specs tighten as your perspective of the next generation technology that's coming?
Well, yeah. What we're doing in that sense is a little bit like the iceberg. So everybody is seeing the IP, and maybe we'll talk about the IP. But we are filing a lot of patents, but there's a tremendous amount of know-how that's behind that, and this ability to, the hydrogen-based layer transfer that we've been patenting first time 1995 now is in the public domain. Okay. And everybody, you see a lot of publication, everybody is doing and publishing, especially in R&D, that can be layer transfer and so on. But that's not the end of the story. The end of the story is like bringing it to a large volume and being able to push the productivity of that process, keep the yield in the very high level, and being able to integrate different layers. All is the key. Our process is based on simply bonding a wafer that's been implanted, and when the bubbles are growing, then since we have bonded it, then it transfers, and the film we have been implanting is transferring onto the other substrate where we make the wafer bonding. Very simple on the base, but if you want to make it successfully industrially and with different thickness, different layers, different type of orientation, different type of substrates, the know-how we have into the industrialization of that and the capacity to make the wafer bonding with a high quality, because this bonding has to be very strong, very uniform, perfect around the wafer, is the key to drive the uniformity we're bringing at the end.
I see. Thank you for sharing, Chris. So going beyond silicon now, and I'd like to talk about heterogeneous and power. We had of course, we just briefly discussed about the compound and power materials. How do you view the role of engineered substrates in silicon carbide or gallium nitride power electronics and high volume applications?
Well, on that one,
high voltage applications.
It's difficult to speak in the past in that one because the jury is still out, and we are still competing, fighting, and making sure that our technologies is bringing value to the customers. So, but in a nutshell, what we saw is that silicon carbide is a fantastic material, and Wolfspeed and John Palmer, and I think I want to give really a high credit to what John has been doing for silicon carbide in the past. They pushed the limit and they pushed silicon carbide to a level that nobody was believing they could bring it. But still, to grow that fantastic substrate, you need to put some material into a furnace for 3 weeks at 2,500 degrees, creating a lot of CO2, by the way, and doing that. And the productivity is pretty low. And that's a little bit difficult to manage and to do. So when you have that fantastic crystal, talking to some of our historical customers, they said, this crystal is great, but the productivity and the usage we can do with it is not enough. So we took it as an active layer and see where we can bring it. For the story, for the silicon carbide, as everybody knows now, we transferred that mono silicon carbide onto high conductivity polysilicon carbide to be able to make the best of it in terms of vertical conductivity. But more generically speaking, these 3-5 materials have great properties, but suffering from productivity that is a little bit low. Then cost at the end is questionable. So our job, number one, is to say, can we bring silicon carbide into silicon? Can we bring GaN into silicon? Can we bring GaN into some material that is easy to work with and easy to integrate? Can we bring 3-5 into the foundries that are making the volume today? It's kind of the starting point. And so this is where the engineered substrate try to make a difference. Can we put GaN and silicon and make only the energy efficient device on gallium nitride and all the device around on the silicon that we know since so many time? That's the approach we're taking today into our developments. And as I said, this is happening now.
Christophe, so looking at the 3D and chiplet era, has heterogeneous integration, well, of course, now it has definitely accelerated and playing a massive role in AI applications, but how can substrates help optimize interconnect density, thermal paths, and co-design across dies?
Well, we look at it, of course, with our engineered substrate lens. And if you look at the technologies that are involved and used into the 3D integration, it's pretty much like playing with layers, bonding wafers together, processing one wafer, second wafer, and then integrating the layers. And at the substrate level for engineered substrate, this is exactly what we've done in the past 35 years, pretty much. So we look at it two ways. Is number one, can we take the technologies that we are using to make the engineered substrate and bring them into the fabs of our customers and look at if there is any business model that we can involve bringing these technologies? That's one. The second aspect is, can we prepare our engineered substrate to make them easy to transfer the layer after the bonding? And that's the last technologies that we are developing. We call it transistor layer transfer. And what we try to integrate into the structure of our engineered substrate is kind of a debondable or transferable layer that after you bond your wafers for the 3D integration, then you isolate with a laser from the backside and kind of magically that layer disappear and you recover the substrate, but the process layer stays on the other side. Why it brings a key advantage is that still we can protect the thickness uniformity by doing that. And when we are protecting the thickness uniformity, we will be able to have a very high density of interconnects because they're all linked to the thickness and the control of what is transferred. So this is really what we are developing now. So this is a topic where this is what my teams is accelerating on a daily basis.
Today, okay. Marvelous. So let's switch into the manufacturing quality and scale discussion. So, one of the key elements is, of course, metrology versus, or let's say, and variability control. Which metrology or inline controls have been most impactful for tightening thickness, box, and resistivity distributions at, let's say, 200 or 300 millimeter?
Yeah, definitely. I think is a thickness measurement, so ellipsometry, because we've been able to work with. In that case, we worked with KLA But KLA has had the good idea, I would say, or they really supported us very well in taking platforms that were designed to measure a thickness for device in small box, and to get a little bit away from that and create machines that were really designed to measure as many points as possible, the fastest way onto the wafer, and adjust their metrology platform to bare wafers, so that we could really bring a high productivity on measuring the thickness, which, as you said, relates to variability of the layers we are transferring. So it's been very helpful in terms of optimizing the uniformity of the silicon, of the box layer. But with these advanced ellipsometers, we are able to measure the index, we're able to measure in multiple diameters, we're able to measure things and interface contribution at the end. So very powerful.
And if you look at like cost performance trade-offs, where do you see or where are the biggest levers to improve cost per function without compromising substrate performance and reliability?
Well, clearly it's about bringing value to the end customer, and we always take that as a metric when we develop the product. So from the beginning, to intercept the market, we look at what's the maximum cost we can come with. We call it design to cost. And the solutions that are not compatible, we drop. And of course, if we cannot find any, we drop. I mean, that's very important. But the most important is the simplification we are bringing at the device. So we bring already pre-processed wafers where the active layers is isolated from the bulk, whatever this is silicon or compound. So meaning that isolation has not to be done in the device processing, and also immediately by lithography and so on. There is some overall die-to-die isolation. One example is in the power SOI I want to give. So in power SOI, we come with a substrate that has already the thick active layer isolated from the bulk, meaning that you can make smaller die and you can make them closer to each other without any latch-up. Latch-up meaning interaction between the NPN of a neighbor die that are going to block the devices. And thanks to the total isolation, this is a big advantage in terms of density. And maybe you can have die up to 50% smaller, which is huge in terms of cost saving at the end. That's one. I mentioned another one, which is the redundancy. If you can get rid of redundancy because of the very good reliability of your device, then this is a big benefit in terms of cost.
And, one of the key words you mentioned about explaining the future of semiconductor manufacturing was green. So I think it's also very important that we also discuss about the sustainability and circularity of things. So looking at, material sustainability, what are Soitec's priorities around water or energy use, consumables, and waste minimization in substrate manufacturing?
What we're doing here, we're focusing on CO2 emission and water. These are two main elements. In CO2 emission, we initiated one program which is called Green Innovation. Green Innovation meaning that usually when we make decisions into process steps or structures, we look at performance, we look at cost. Now we look at performance, cost, but also environmental impact. And we even took some decision the first time last year where we did not qualify one process that was really bringing performance. Cost was okay, but it was not really okay in terms of the impact. So we did not use that technology. For water, there's a great work that is done by reusing the water. So we reuse a lot of the water in the fab. And in the past 2 years, even though we increased the capacity, we did not increase the usage of the water. So that's a very drastic measures that are taken by our operations to make sure that even though we are producing more wafers, we are not using more water.
Fair. And what about in terms of reclaim and recycling? I mean, how viable are reclaim or reuse pathways for engineered substrates? I mean, where do you see the most promising secular economy wins?
But first of all, if you look at our smart cut technology, there is inherent recycling in it because the donor wafer that we are transferring, the thin layer that we are transferring from the donor wafer to the receiver, we are repolishing to reuse many times. In the SOI, we use up to 10 times the initial wafers. In compounds, we look at using more than 20 times the same wafer. So that wafer that's been processed with a high energy spanning and shipped to our site, we are now smart cutting, if I make a verb of it. We are smart cutting and then we are locally repolishing and reuse it multiple times. So that's saving a lot of the energy that is used to create the crystal. In terms, that's the first part. In terms of recycling at the end, well, we are bringing an active layer on top of silicon with an insulator in between. So in many of the applications, and especially in the 3D, we aim to recover that base silicon wafer and make sure that we can use it as a new support for the coming. It's just a transport wafer, and we want to use it as a new transport wafer.
Fair. I'd like to talk about also your collaboration and ecosystem strategy plans. So the CEA-Leti partnership playbook is something I really would like to discuss. Is what makes the Soitec CEA-Leti model effective? I'm presuming one is location, but also how do you structure co-development with customers to de-risk adoption?
Well, yeah, the relationship with CEA-Leti, first of all, is a very long-lasting relationship. So the smart cut process has been initially developed with them. So on top of that, then we did it on silicon. We pushed the limit. We're creating the models to understand the physics of what we're doing. And then we look at new materials. And we had multiple PhDs addressing the topic. And PhDs bringing really a very complete understanding of what's happening from the mechanics, but from also the technological implication into the fabs. So all of that we have at the bank, and we use it as a very strong asset to further develop and bring additional values. But the really key moment and pivotal moment into that is in 2017, we created Substrate Innovation Center. To create that Substrate Innovation Center, what we did is to bring Soitec core technologies, manufacturing-like technologies into the Leti. And so we can basically process wafers very close to the specification of our manufacturing. But when we want to de-risk, use one of the alternative technologies that we can find into the Leti clean room and Leti ecosystem, and very quickly simulate or very quickly enable the demonstration prototypes, like processing maybe 70% of our usual quality, and bring one additional step that we can find into the Leti to make the first prototype, and then immediately starts the understanding of the physics that's behind the models and so on to refine the initial empirical test that we've been doing by a lot of additional understanding and maybe fine-tuning the recipe. The benefit is that we are not bringing the risky piece into our clean room, into the manufacturing, but we bring our manufacturing way of doing close to the research or alternative technology. The second benefit is that we can generate very quickly prototypes to send to our champion customers and validate what we are doing. And that's been allowing us since 2017 to go very quickly. For example, in silicon carbide, it's been 4 years from the idea to bringing it to our fab, which was very quick.
And if you look at of course, the finalization of all of this whole process, which of course will go into the standards and certification, how do industry standards or joint qualification frameworks speed time to market for new substrate variants, or does it actually hinder the situation?
Well, when we can demonstrate the value very quickly from the beginning, it's really helping, because then it means that we are immediately starting the FMEA. So all the failure analysis and the link between the substrate and the device is started very early on. And with the champions first, then deployed to all the different customers that are interested. And as we are aiming to create standards into the market, meaning we really want to deploy these technologies to all different players to make sure that whoever then is getting the leadership for one generation or the other, we are able to support all the players with our substrates. The very early starts at the prototyping level is really boosting the adoption of the technologies. That's super important, because we can get maturity level much earlier, meaning that the customer is going to yield on our material much earlier, and that's really accelerating the whole thing.
Interesting. Thank you for sharing that, Christophe. So I want to talk about the transition as well that some people out there are also may be facing, is going from that PhD education to the executive MBA education. How has combining a microelectronics PhD with an INSEAD MBA influenced your approach to maybe like portfolio bets or organizational leadership?
Well, yeah, it's first of all, I want to stay humble on that, because just one example, and I don't want to make a rule of what's been my experience. But well, I think the MBA has given a new angle of what I was doing, meaning that as a PhD in the technology and growing into the company, you really see that the technology is everything. So technology is very important, but that's one element of the global solutions. And the business side, the way the adoption is driven, the collaboration modes that could be made, the IP, the strategic implications are all different elements that the MBA is pushing on. And that are really completing the technology view that's coming from the PhD and growing as a product engineer. So overall, and on top of that, of course, innovation management, people's management, and so on is also completing that very nicely. But I would say the number one element really is to say that the way that the financial implications of the new products, of the innovation, is a very important complement to the PhD.
Yeah. I mean, is that the reason why, of course, there's a connection to like IP and innovation velocity? I mean, you hold more than 30 patents, you've got 30 plus papers, but as Soitec as a whole, I don't know how much IP you guys have, but how do you cultivate a IP-driven culture that still moves fast from concept to product?
Well, that's true. IP is so important in Soitec. We have more than 4,000 active patents. We are bringing basically one per day, in either a new idea or bringing it to a new country and so on. It's important for two reasons. Number one, pretty standard reason is we want to be a leader and we want to drive innovation, and we want to make sure that the followers are not cutting the corners by getting inspired by what we are doing. They can be inspired, but the IP is going to protect where we're going. That's one. But the number two is, in that case, I compare innovation with being French is easy, but I compare innovation with wine.
Yeah.
So when you do wine, well, typically you're going to know many years later if this is a good wine or not.
Yeah.
And I think for innovation, it's a little bit the same. It's going to take 5 to 10 years to bring new materials, new structures, new everything into manufacturing, and know at the end that was really the right things to do with the customers. But when you are pushing filing patents, well, basically you are challenged on the innovation you're doing. You are challenged on is it really changing the knowledge? Is it really pushing the limits?
Yes.
And so what we do is to compare how much we invest and how much patents we're doing, and we aim to have one patent family per million euro we invest, which seems to be a right indicator to say and to anticipate if your innovation is at the right point.
Fair. Christophe, you mentioned how the N+2 model plays a key role in terms of future outlook and advice. So looking at a 5 to 10 year roadmap, from your perspective, which substrate breakthroughs, be it material stacks, bonding, surface engineering, do you feel are most likely to redefine performance in compute, RF, and power?
Well, I think this is the baby of the moment that we are growing, but the ability to bring easy to transfer layers in a 3D world and in a heterogeneous integration world, I think it's going to play a very important role, and that's why we are pushing very hard at the moment. Then the asset of all the optimization for performance, power, and cost that we've been putting with the engineered substrate in the past, in a view of system optimization, total system optimization is going to be very important in the future. And we need to come up in some further optimization of what material we are bringing for what functionality in a global system optimization. And an interesting thing, in that case, the diameter limit is no more there. Because you can integrate together a device that's been done on 6-inch with a device that's done on 300 millimeter, and it doesn't matter at the end with the full integration. And this will bring some more focus on some of the solutions that were not fully deployed because of the diameter limitation, and that needs to be re-examined in terms of a total system optimization.
Fair. Christophe, thank you for this marvelous discussion. I mean, what advice would you give to other material innovators out there? I mean, what guidance would you offer researchers and startups aiming to cross the valley of death from novel wafer concepts to high volume manufacturing?
Well, first of all, just for the joke, but if they are competitors, there's no advice I want to give them. But in a general sense, making sure that the material innovation is addressing a challenge at the system level as much as possible, and get rather pull than push in terms of technology innovation. And the second one is really to anticipate the qualification time as much as possible, because this is the difficult piece.
Yep.
You develop a new type of technology, you come to the product, you need to qualify, and this is more and more difficult to get qualified as a product level, at the system level. But then this qualification time is a time where you have a hard time to load your factories. And so everything that can be anticipated is going to help a lot in terms of the return on investment. That's for sure.
And, one interesting one is also if you could go back to the Christophe who just came out of his PhD, what advice would you tell him then, being the man you are now?
Wow. That would be interesting to come back to that guy and stay there.
Yeah,
and
you want to stay there, go back in time.
And do it again. But I would say again, be confident that you can change things and become who you are, basically. So that's
More than a person. Yeah, the last person, I can't remember who it was. Well, one person who said, if I could go back to that person, I'd say, buy Bitcoin. But that's fair. We have a tradition on the show, Christophe, where the last person leaves a question for the next person. So the question that was left for you from the last interviewer is, what are you most excited about right now?
Making sure that everything that's been done in the past 30 years is amplified and accelerated to create 10 times more in the next 30 years. Because we see the big acceleration into our technology. If you turn back and see the speed of things coming since you connected first into the internet, to the first connection with your smartphones, with electric cars, AI, and so on, you see that acceleration of the technologies. So making sure that everything we've been doing is going to generate 10 times more in the coming 30 years. I mean, that's excitement.
Is that what's keeping you going? Is that what gets you out of bed in the morning to keep pushing?
Well, keep pushing, competing, pushing the limits.
Yeah,
that's the most important.
That's the game for it.
Yeah,
Christophe, thank you so much for joining us on the Semiconductor Leadership Podcast. I think that the in summary is anything can change during a certain situation or matter. But thank you to everyone who joined in on the show today. If you want to follow Christophe and get more insight on Soitec, his LinkedIn profile is just below here, and Soitec website is just below here, so you can check him out and learn more about the SOI world. As we always say, thanks for tuning in. And please, if you found the podcast of interest, click that reshare button, because at the end of the day, it takes a village to raise a chip. Other than that, see you on the next episode, and take care, and bye for now.